Hello everyone! We're going to continue on with acid-base reactions. Our goal today, or at least for this video, is to get through the different types of acid-base neutralization reactions because there's actually more than a few different types that you're going to see on your AP Chemistry exam. Also, I want to get through a few more types of metathesis reactions, which are specifically called gas-forming reactions. So we'll look at those too. The one thing that I need you to tell me, because I don't know how much redox you've done, because that's the next type of reaction that we'll cover in Chapter 4. So if you know how to find oxidation numbers, if after you've watched this, if someone would post on the blog, yes, we know how, yes, we remember all of the rules, and if not, then post on the blog, no, I don't remember, please, in the video tomorrow, teach me how to find oxidation numbers, okay? So somebody please tell me that, or all of you tell me that, I don't care. I just need to know, so that way I can know how to make your video for tomorrow during class. Okay, so in class we left off here. I have water plus ammonia, and ultimately these two will react to produce ammonium ion and hydroxide ion. With this, remember it's a reversible reaction because I don't have a strong acid or a strong base in either one of these, so I'm going to have some type of then reversible double arrow. We labeled NH3 as the base and H2O as the acid earlier in class, and we said that this was the acid because ultimately it's going to donate a proton to NH3, and NH3 is going to be a base, and this is according to Bronsted-Lowry theory because we're talking about proton transfer here. NH3 is going to be a base because it will accept a proton. Now, conjugate acid versus conjugate base is the definition that we were focused on right before the bell rang. So let me give you a definition of conjugate acid and conjugate base. A conjugate acid is a substance that will accept a hydrogen ion. So a conjugate acid is a substance that will accept a hydrogen ion, okay? A conjugate base then is a substance that will remove or release a hydrogen ion. So a conjugate acid is a substance that accepts a hydrogen ion, and then a conjugate base is a substance that removes or releases a hydrogen ion. So we said this was the acid, this was the base, and according to my definition of a conjugate acid, which is saying that it's going to accept a hydrogen ion, then my conjugate acid in this case has to be NH4+, because over here I had NH3, it accepted a hydrogen, so that means that this must be the conjugate acid. Plus it's kind of easy to remember it this way. This is the base, so then what it forms is going to have to be the conjugate acid, because if I reverse this reaction, then this is going to donate the proton, which will make it an acid, and then this is going to have to accept the proton, which would make it a base. So you can kind of look at it also in the reverse reaction as well. And then our conjugate base is something that removes or releases that hydrogen ion, so I have to remove some type of hydrogen ion. I was starting off with water, it removed an ion, so that means that hydroxide must be my conjugate base. So it's actually quite nice here that it just labeled right with labeling. Acid, base, conjugate base, okay? So when we talk about reactivity of strong and weak acids and bases, it's really all about how many ions that we have dissociated in water, ultimately. It says when reactivity depends only on the hydrogen ion concentrations, strong acids are going to be more reactive than weak acids. And that's because a strong acid can completely dissociate, meaning that I'm going to have more hydrogen ion concentration. I'll have more of this because that acid, like HCl, is a strong acid. It's able to fully dissociate every time into hydrogen ion and chloride ion. But if I compare that to like acetic acid, which is a weak acid, I'm not always going to get the hydrogen ion from acetic acid to dissociate. So strong acids are going to be more reactive than weak acids are. Sometimes reactivity of an acid can depend on the anion concentration. So for example, hydrofluoric acid is considered to be a weak acid, but it's actually very, very reactive. So we consider it to be weak, even though we don't necessarily see it macroscopically that way. Sometimes we can see it to be very reactive. This we don't care so much about, just because we're usually focused on the strong acids, and then if it's not a strong acid, you immediately say that it's weak. We're not going to get so specific into this with our AP curriculum. Okay, so let's compare using some particle diagrams. Let's compare some acid strengths. You're given the following acids. We have HX, HY, and HZ. And it says that all of these represent aqueous solutions of the following acids with water molecules omitted. So I'm not showing the intermolecular forces that these play with the water molecules. Your goal is to rank the acids from the strongest to the weakest. So I would like you to try that. And after we try that, I'll make this the first slide that we look at to go over it in your video tomorrow while I'm gone, okay? So rank these, HX, HY, and HZ, in order from the strongest acid to the weakest acid. And then I would also like you to explain why. So give me your ranking and then be able to make sure that you're able to explain why to me. Okay, I also would like you to try these things. And this is just the identification of strong versus weak electrolytes. So the table 4.3 in your book gives you examples of strong electrolytes, weak electrolytes, and non-electrolytes. So any ionic compound would be considered a strong electrolyte. There's no ionic compound that's considered weak. There's no ionic compound that's considered a non-electrolyte. All of the molecular compounds, if it's a strong acid or if it's a strong base, I mean strong bases are just ionic compounds. But if it's a strong acid, it's considered to be a strong electrolyte because it will dissociate completely. If we're talking about molecular compounds and specifically their weak acids or weak bases, we consider those to be weak electrolytes. And that's because they can dissociate into ions. They're just not going to fully dissociate into ions. And actually, they're very poor at dissociating. And then any other compound that's molecular, that's not a strong acid or a weak acid, weak base, so any other molecular compound we classify as a non-electrolyte, so like sugar, for example, or any hydrocarbon for that matter. So these two questions, I have classified the following as strong, weak, so a strong electrolyte, a weak electrolyte, or a non-electrolyte. Okay? And then I also have the second question. Rank the following compounds that are dissolved in water in order of increasing electrical conductivity. So if I'm ranking them in order of increasing electrical conductivity, I should have non-electrolytes, followed by weak, followed by strong electrolytes. So please try these two. We'll check them again at the beginning of class tomorrow. Let's talk about neutralization reactions. When we hear neutralization reactions, we typically just think, okay, I'm going to have an acid, it's going to react with a base, and I'm going to produce some type of salt and water, okay? That's just the very generic neutralization reaction. But there are actually a few different exceptions to neutralization reactions that we need to go over. So if I have an acid, I have a base. Here's my salt, because CH3COO, this would be C2H3O2 minus, that would be acetate. And then my sodium ion, so this would be sodium acetate. That's going to give me salt. And then I have my water. So acid plus base makes salt and water. That's the very generic term. When a strong acid reacts with a strong base, then we're going to always get, because remember our reaction should always be considered in net ionic reaction terms or net ionic equation terms. So let's say I react a strong acid and a strong base. I have hydrochloric acid reacting with sodium hydroxide, and since I have an acid and a base, it should give me salt, which is sodium chloride, so we see that, and water. I have that product. If I break this molecular equation and write it into the complete ionic equation, meaning that now I'm breaking up any of the aqueous ones that I can into the ions. I have hydrogen ion, chloride ion, sodium ion, hydroxide ion. I'm keeping water intact here on the product side, but I can break apart the sodium and the chlorine from sodium chloride. We cancel out our spectators. So in a neutralization reaction, really all we're doing is producing water. I have hydrogen ion concentration, I have some hydroxide ion concentration to produce water. That's really the end-all be-all in neutralization. And that specifically happens when a strong acid reacts with a strong base. It's different if you have a weak acid with a strong base, or a strong acid with a weak base. You may not always get this. So let's talk about, let's actually talk about some of these different possibilities that we may see. Okay, so with acid-base neutralization, so we just talked about first, straightforward, I have acid plus base, and specifically strong acid plus strong base makes salt and water. Polyprotic acids, though, are really, really tricky. And that's because you have to keep keywords that are going to be thrown out when you're having to write a chemical reaction out. So it says, if the sentences say, or this should say, if the sentence says, that the base is in excess. So if I have excess base that's reacting with an acid, it says all of the hydrogen ions will react to produce water. So remember how today we talked about how polyprotic acids, they take off an ionizable hydrogen one at a time. That's how it works. If I add excess base, if I say, I'm going to react to that acid that I have, but I'm going to flood a ton of base with it, then ultimately what you're doing is you're kind of skipping the step part where they're all just going to come off at the same time. So let's maybe look at an example of this. Okay, so maybe an example could be, let's say that I have, just kidding, dilute, I need the pen. Okay, let's say that I have, or I give you the sentence, dilute sulfuric acid is reacted with excess, let's use sodium hydroxide. Okay, dilute sulfuric acid is reacted with excess sodium hydroxide. So I have sulfuric acid, we know that's H2SO4, that is a polyprotic acid, it has two of these ionizable hydrogens here, and I'm reacting that with NaOH, sodium hydroxide. But I'm reacting that in excess. So if it said without the excess, I would have to show this in step form. So I would have to do H2SO4 plus NaOH will make NaHSO4 plus HOH, which is just water, right? But in this case, because it says excess, all of these hydrogens are going to come off at the same time. So because of that, because they're all going to come off at the same time, I'm going to get Na plus then the ion that's left over here, which would be sulfate. So I have sodium sulfate, but that should be Na2SO4, plus then water. Okay, but then I see that I have a problem because it's not balanced. So I should have a 2 in front of the NaOH, and we should have a 2 in front of the water. There we go. Okay, so any excess one, we're going to have to take all of the hydrogens off of that acid if it's a polyprotic acid. Okay, let's go back and look at part B. If the reaction happens by mixing equal numbers of moles, so if I have an equal number of moles for the acid and I mix that with an equal number of moles for the base, then it will follow this polyprotic acid trend where it's only going to come off one hydrogen at a time, okay? So if I were to do the exact same equation over again, except instead I said dilute, and this is maybe something that you would read as an equation. So it says dilute sulfuric, actually let's not even say dilute, let's just say, let's say equal number of moles, because that's really what it is. You may see a problem that says equal number of moles of sulfuric acid and sodium hydroxide react. So maybe this is a sentence that I give you, and I ask you, write the net ionic equation. Actually, let's not even do that. Let's write the molecular equation that's balanced based on the following sentence. So equal number of moles is my hint, and since it's equal number of moles, that means that the hydrogens are going to come off one at a time. So it's going to follow that polyprotic trend of just one ionizable hydrogen coming off at a time. So I would have H2SO4 plus NaOH. Okay, now this H2SO4 and this NaOH, one of the hydrogens is going to come off. So if one of them comes off, it's going to leave me with HSO4 minus. So then that hydrogen is going to go over here with the OH, giving me a water. And then that HSO4 minus is going to come over here with sodium. So my product should be sodium bisulfate plus water. Okay, and then I'm going to make sure that it is balanced, and it already is balanced. Okay, so that's what I mean with the difference in just, you have excess, all of the polyprotics, all of the ionizable hydrogens from a polyprotic acid will come off. Equal number of moles or equivalent molar concentrations here, I'm going to see that one of the ionizable hydrogens will come off at a time, okay? The last one I think that I have up here, on number 3, it's just important to know concentration. If they give you 0.1 molar of something, and then they give you 0.2 molar of something, and they tell you that that's in equal volumes, then they're trying to tell you that there's a specific mole-to-mole ratio that they want you to use there. We're going to focus on number 3 a lot more when we get into the acid-base chapter, which is like chapter 15, 16-ish. So I'm going to kind of hold off on number 3, but right now I just want you to note, let's remember concentration as being important, but we'll get to concentration when the acid-base stuff really comes into play more, okay? But polyprotic acids is huge. I will give you equations that have to deal with these, or you may have just a really simple, straightforward, strong acid plus strong base makes salt and water. Okay, let's talk about gas-forming reactions. There's a few different types of gas-forming reactions that we need to know. These are still considered to be metathesis reactions, but some of these gas-forming reactions don't give us the product that maybe we would have expected it to give us. So, let's say, for example, that we did calcium carbonate and hydrochloric acid. So maybe before, if I did this reaction, or if you were to do this reaction before, you may have assumed that it would have given me maybe carbonic acid. I would have gotten H2CO3 plus calcium chloride, but that actually doesn't happen. So, in any type of reaction in which a carbonate or a bicarbonate reacts with an acid. So in here, I have a carbonate compound, and it's going to react with an acid. So any reaction that has a carbonate compound and an acid will always produce salt, carbon dioxide, and water. And this is just something that we're going to have to know. And that's because carbonate wants to usually break down into carbon dioxide and water. Okay, and I actually put this in words on the next one. Okay, good. So when a carbonate or bicarbonate reacts with an acid, the products will always be some salt, carbon dioxide, and water. So here I have calcium carbonate, like we just saw, reacting with hydrochloric acid. I get salt, carbon dioxide, water. Here I have sodium bicarbonate. So if I see CO3 or if I see HCO3, and as soon as it reacts with an acid, I will get three products. NaBr is my salt, carbon dioxide, water. So this is one type of gas-forming reaction, but again, we have a couple different types of gas-forming reactions, so let's look at the next one. So similarly, anytime that we have a sulfite, remember sulfite is SO3, so anytime that I have a sulfite, it's going to give me products that are very similar. I'll have a salt that's formed, so here's, let's say I have strontium sulfite reacting with hydroiodic acid. The salt that I'm going to get is strontium iodide. I see that here. I'll get sulfur dioxide and water. It's because really the only difference between a carbonate and then the sulfite reactions, or carbonate and bisulfite versus, carbonate and bicarbonate and then sulfite, is that in the carbonates you're making CO2 and in the sulfite you're making SO2. So really very similar trend, but a little different. Okay, let's do, actually we have two more. Okay, in this case, let's say that I have a sulfide. So let's say that we have sulfides. Any sulfide plus an acid, is going to make salt, so the salt here, and I'm going to make hydrogen sulfide gas. Any sulfide that reacts with an acid, because I don't have that on here, guys, so any sulfide that reacts with an acid will make some type of salt and hydrogen sulfide gas. So in this case, I have sodium sulfide reacting with sulfuric acid. So I have a sulfide and an acid. I have my salt, and then I have this hydrogen sulfide gas. This reaction is very popular, or hydrogen sulfide gas alone is very popular because H2S, hydrogen sulfide gas, is what gives rotten eggs that smell. So that's the smell. If you ever have really nasty rotten eggs, it's because it's producing this hydrogen sulfide gas. So this one's actually really nasty. Ugh. Okay, so far we have three gas-forming reactions. We have the carbonate or bicarbonate, and if it reacts with an acid, then that means we're going to get carbon dioxide, salt, and water. If I have a sulfite that reacts with an acid, I can get sulfur dioxide, water, and salt. If I have a sulfide that acts with an acid, or reacts with an acid, I'm going to get salt and then hydrogen sulfide gas. Okay? So, just as a review, I have this on here. Any sulfide plus any acid, we just said. Any carbonate plus any acid, we already said. Sulfite plus any acid, you can fill that in. But we have one more. Okay, my last one is any ammonium salt. So if I see NH4 in a salt plus any strong hydroxide, so all of these have acids with them, but now let's say that I take an ammonium salt and I react it with a strong hydroxide. Then that's going to form water, salt, and ammonia. Okay, so that one's going to form water, salt, and ammonia. So any ammonium salt plus a strong base gives me NH3, gives me H2O, and gives me some salt. And the only reason that that one is different is because now we're reacting it with a strong base instead of reacting it with an acid. Okay, I think we are up to oxidation reduction reactions. Okay, I'm stopping here. Our video tomorrow in class is going to start covering these redox reactions. I think, like I said, that you probably have done oxidation numbers, but if you flew through it, I don't want to fly through it right now. I want some practice on doing oxidation numbers. So let me know if that's something that you remember or if we need to kind of go slower on that. And then we'll hit up redox reactions and single displacement reactions tomorrow. Guys, if you have any questions on anything that you saw, let me know. If not, I won't see you tomorrow, which I'm very sad about, but you will see me in your video. And email me, post on the blog. I will be here after school tomorrow, so if you do have questions and you're like needing to actually see me to explain them, just stop by tomorrow after school and I will help you. Have a really great night, guys. Bye.